so last year we did our first roadshow, and I know you guys were, I think you guys were there. Recognize your guys' faces. That roadshow was all based on a quadcopter, and it ended up being one of our most popular events, probably one of our most well-received events as well, because it showed people how we use the tools on our projects. And so instead of like a demo situation, right, it's a little bit unrealistic. And a lot of people got good information out of that. That roadshow focused on 3D printing almost entirely. And it focused on things like FDM versus PolyJet, the differences between the two technologies. It focused a lot on some of the manufacturing applications that we do alongside the 3D printing. So instead of just using a 3D printer for, I guess, a prototyping machine, we use it as a machine to create shapes that allow us to do other types of manufacturing quicker and more cost effectively. Things like 3D printing short-run injection mold tools, 3D printing carbon fiber layup tools, 3D printing urethane casting molds, stuff like that. And everything that was done inside that presentation, which you see up here, was all done on a single platform, and that's SOLIDWORKS. Who in this room is a SOLIDWORKS user or has used SOLIDWORKS? Only a couple hands. So I'm from Salt Lake City, and in most of our territories, we sell SOLIDWORKS. And so most of the people that come to our events are heavy SOLIDWORKS users. But every time I come up to Portland and Seattle, I'm put in a room with people who normally use like CATIA or Inventor, or what other CAD tools are you guys using? ProEngineer? Oh, I'm sorry. I actually learned on ProEngineer. When I started university in 2004, we had Wildfire 2.0, and it was on an old Linux machine, and it looked like a piece of software that was written before I was born, and it totally turned me off from CAD. I don't relate to this. And then we got SOLIDWORKS in my senior year, and then I saw the light, like, oh, CAD is actually useful.
Decades ago, one of my favorite releases was the one where you hit the save button and it would crash.
Oh, I like that one.
Short-lived release, but
hey, that's a feature of SOLIDWORKS in some service packs. It's like the McRib. Sometimes you get it, sometimes you don't. All right. So for this roadshow, I enjoyed doing this myself because, you know, if I get to create a quadcopter for my job, I'm going to do it. So this year I wanted to do another roadshow. I said, can I do an RC car? And they said, sure. So I got pretty lucky there. One thing I wanted to do differently was I wanted to focus more on the design aspect, all of the steps leading up to the 3D printing. So for this presentation, we're going to focus about 30% on the 3D printing, but also 30% on reverse engineering and another 30% on the analysis-driven design, and then the extra 10%, I don't know. I don't know where that went. Probably fun time. One of the things that you're going to see here during this next a little bit over an hour is something I call a digital workflow that's on multi-platforms. So instead of staying within that SOLIDWORKS world, which keeps you pretty limited, or instead of staying on the one CAD platform, which has a lot of tools, but if you're staying within one platform, you're always going to be a little bit limited. We're going to see multiple platforms working together side by side. And that's a huge theme of today's process is how can we bring together a lot of different pieces of software and use each of those for their own strengths, and how are they going to be tied together? What does that workflow look like? I will say right now, we are going to have a lot of content, and I'm going to go through it a lot quicker than normally, but I also encourage you guys to have questions and ask them when they come up. So if this is more of a discussion, I would appreciate that. Also, if you guys can please laugh at my jokes, I would appreciate that, because I am recording this. So this is the version that's going to go up on YouTube, and it's going to ruin my reputation on YouTube if I tell jokes and you guys don't laugh at them. I'll say, all right, so here's the scenario for Project RC. GoEngineer is pivoting, and we are going to enter the RC market. This is the scenario here. We want to create aftermarket parts for existing RC car chassis. So I know at least one of you recognize that as being a Traxxas / Anybody else here into RC cars? Yeah, I'm not either. I wasn't until I started this project. I was like, this is actually really cool. And I go to the hobby shop and they have indoor tracks and it's awesome. And I start thinking, oh man, I could really get into this. And then I remember that my wife already thinks I'm a child. And so if I start showing up with these at home, you know, it's probably not going to go over very well. One of the things that we want to do with our products is we want to make sure that they are all designed efficiently and smartly, and they're all optimized. There's a lot of thought behind our designs. We want them to look good, but we also want to be able to prove that, you know, we've put a lot of time and analysis into an effort into creating quality parts. And so everything that we design is going to be based on this analysis-driven optimization, which is something we're going to talk about. The initial product line is going to be low volume and customizable, so it's a perfect scenario for 3D printing. 3D printing is its most efficient at one single part, right? And as we start to scale up, 3D printing starts to lose its efficiency. So at least as initial release, what we wanted to do was create a car like this that we could bring into like a focus group or put it in front of prospective customers and say, this is what we're capable of doing. This is how we design this. This is the thought process that goes into our parts. You know, this particular chassis might not be optimized for mass production, but we're capable of doing mass production designs, but we're also capable of creating these very one-off customized parts as well. So there's some brand visibility and marketing that comes into our use of the 3D printing today. Future plans might include high production if we're successful in our efforts. So that's always something in the back of my mind. When I'm printing parts, I have to ask myself, what's the end goal of the print? Is it going to be a prototype? Okay. Is it a prototype of a part that I'm eventually going to injection mold, or I'm eventually going to cast? Then I have to design for the cast version, or I have to design for the injection molded version, right? But if the end goal is a 3D printed part, then I can design for 3D printing. And the design for manufacture rules for 3D printing are a lot different than the design for manufacture rules for injection molding. Does that make sense to you guys? So the car that we based it off was a Traxxas Slash. We based it off Traxxas because basically they're the leader in RC cars as far as my little bit of research found. And so we wanted to pick somebody that already had an established market that we could poach. We could build our aftermarket parts on this. It felt really nice to go into the hobby shop and say, what's your guys' most popular car? I'm going to buy it. And they're like, okay. And they said, you know, what's your price range? And I said, I'm not paying for it, so what's your most popular car? And the thing ended up costing about $400. And I didn't even have to get that one. The $400 one had like upgraded motors and stuff like that. It isn't even important, but I have to buy the best, right? Here it is underneath the shell. And this is what we're going to be reverse engineering and building our aftermarket parts for. All right, so it's actually a really good design, and it's optimized for injection molding. And you can see the chassis of the car that we purchased here. So what's the workflow going to look like? We're first going to reverse engineer this existing platform. What we want to do, and you guys are probably going to start to have some questions at this point because you don't really know the end goal, you don't know the process. So if you do have questions, again, you can ask them, but probably understand that I will probably answer them. We're going to reverse engineer the existing platform. The whole idea of reverse engineering is we just need to create a digital model of something that is already, you know, three-dimensional reality. We need to create a digital model that we can use as a guide to design new parts off. Once we have those parts digitized and we can start doing our own designs, we need to go to our analysis-driven design step. And you'll see how this works. And to be honest, this is going to be my favorite part to talk about. And I'm guessing that there's nobody in this room that has ever done this analysis-driven design before, the way we're showing it. It's really nice to be presenting to a group of people and knowing that I have something that probably nobody in here has seen before. There's going to be something new for everybody in this room, I promise. What analysis-driven design is, just in a nutshell, is it's a first pass design where we take, say, critical mounting points on a chassis or a bracket or some other component. We build a working envelope around those, okay? And then we set up an FEA study, so we do load cases. And then that FEA study iteratively whittles down that working envelope to a minimum, most efficient shape. We call it topology optimization, okay? So that's how we turn something like this into something like this. And he eliminates that first pass guess. Who in here is a designer? Like CAD designer, engineer, you design parts. You're given specs for a part. Say it's a bracket, and this bracket has to connect this thing to this thing. Has to do something in between it. That's the bracket you're going to create, right? So the mounting points, but what's in between, the shape of your bracket, you basically take a guess initially, right? You take a guess, you do an FEA analysis after you do your guess, and then you might start to change your shape at that point. What this is doing is it's going to give you that first initial shape and eliminate that first guess. So right away, immediately, you're heading down a path that is going to be the most rigid or the most stiff or is going to target a certain mass. Okay, so after that initial step, you have a shape. That's where you take it into SOLIDWORKS or Pro-E, unfortunately, or Inventor or CATIA, and you start to do your more manufacturable, more functional, more detailed design. And then you're going to go to 3D printing, ideally, and prototype that. You're going to test it. You're probably going to break it. You're going to iterate it. The more iterations that you can fit into a certain monetary budget and time budget, normally the better your product is. You guys agree with that? The more tries you get at something, eventually you're going to get to the best. And that's where 3D printing really makes its name as a rapid prototyping technology. So here are the vendors and products that we're going to use for this multi-platform presentation here. We have CREAFORM, which is the manufacturer of the 3D scanners. That's going to be our reverse engineering step. Then we have a product called Inspire. Has anybody heard of Inspire? Yeah, see? One person? One person. Have you used it?
Yeah.
Pretty nice, right? I like that smile on his face. So I think it's pretty nice too. We just started repping this software, and the idea of topology optimization is something that's been on my mind for at least a year, and I evaluated a lot of different softwares, and we eventually honed in on Inspire because it has a lot of tools that other topology optimization softwares don't have. I'll be talking about those throughout the presentation here. But that's what gives us our first pass design. And then we're going to use SOLIDWORKS for our detailed design. And then once the detailed design is complete, then we use our Stratasys machines to prototype and possibly even manufacture end-use parts for this. So because I knew a lot of people wouldn't be familiar with at least CREAFORM and SolidThinking, I included just some vendor information here. CREAFORM is headquartered in Canada. Cameron just spent a week in Canada. They had a new product unveiling last week, right? Some really, really awesome stuff. Unfortunately, I'm not allowed in Canada because they have crazy laws.
That's a joke, right?
Sometimes life is a joke, right? We've started repping CREAFORM a little over a year ago now. 2015 was our first full year, and it has been a very popular product. We sold 3D scanners before I was with GoEngineer. I've been with Go for about 6 years now. We sold scanners before that, and we stopped selling them because the hardware didn't meet the expectations of the customers, the marketplace. There was a huge mismatch between the two. And then once these CREAFORM machines came up to date about a year ago, we got back on board because we finally felt like the hardware and the software were meeting the expectations of most of the market. We carry a few different 3D scanners, and we also have 2 software options. Who has experienced 3D scanning in this room? A couple hands. So the whole idea of 3D scanning is it's basically the opposite of 3D printing. 3D printing, you take a digital file and you make it reality, right? 3D scanning is you take a part that's already exists and create a digital model from it. There's a lot of different reasons why you might do that. There's different ways you might do it. Our scanners, they use different types of light sources. One's called a structured light or white light, and another one is called a red laser scanner. The structured light scanner is able to pick up colors, textures, decals, but it's not quite as accurate or precise. Whereas the laser scanner is more accurate, it's more precise, has better resolution, but it doesn't pick up color data. It's one big difference there. These scanners are non-contact. They don't have probes, although they just came out with a new probe version, right? They don't have probes. They're handheld and they're portable. which is a huge asset. And one of the things that we really wanted in a scanner is we wanted to be able to take it to, say, a garage and scan an old vehicle, the entire vehicle, inside, outside, everything, and not have to worry about a probe and an arm and accessibility and stuff like that. Scanning is a multi-step process. So for those of you who have scanned, do you guys agree with the fact that the scanning step is just the first step and it's the easiest step? You guys agree with that? Right, yeah, you got a nice smile on your face. It's definitely a two-step process. So you scan it and that will create a mesh, and then normally you're going to be reconstructing the model. So here's an image of our scan. I normally just wouldn't print or manufacture that directly. Normally what I would do is use the scan and use the software to recreate a parametric CAD file off that. So you can see it does have targets or stickers on the model. That's how these scanners register.
How are the stickers picked, the location picked? Is that arbitrary?
It's arbitrary. They say about every 4 inches or so. So you can see in real time how quickly he's collecting that data. At any point, he can pause that for whatever reason and continue on later. Because he has those targets, he could actually move that transmission housing at any point as well. So he could actually hold it, if he's strong enough, in his hand, move it, and do the outside and the inside of that casing all in one scan. I'll let Cameron answer that after the video.
Does it stitch? So if you go over an area and you inadvertently, because of the angle that you moved it, left the patch out, does it know, and you do a repass, it knows just to patch that area that it missed?
It will continue collecting data over the stuff that it's already collected. But yeah, if you are scanning and you pause it and you start maneuvering the model and you see areas that you missed, you can start it right back up and continue scanning and hit those spots that you missed. You don't have to rescan it and then mesh those later. Does that answer your question?
Yeah.
So Cameron, the question came up about resolution. Can you quickly answer that?
Yeah, so this HandyScan 700, which was the unit we used for this, it will do a global resolution of 8,000, and then you can zoom in on areas and do down to 2,000. Resolution, of course, is different than accuracy. The accuracy that this one will hold, and most scanners are rated over a volumetric accuracy, is less than 1,000. It's 7,000 to 10,000 for that scan.
All right, so there's a few different 3D scanning workflows. Scan to print is the most basic. This is where you might scan a part and then manufacture that or print it as is. So this is used pretty often for things like artifacts. We've done dinosaur bones, handcrafted models that don't have any digital files that exist. Scan to CAD is going to be a little bit more popular workflow, and this is really what we did in this presentation. This is where you're using a scan to create a guide to recreate parametric CAD files, or using a scan to build parametric CAD files off of the scan using it as just a guide. So for example, this part here, this is a scaled down version of a W12 12-cylinder intake manifold. And what the people wanted to do is they wanted to create a new manifold that instead of sprouting sideways, it just went straight up, right? So what they needed was the bolt pattern and the exact size of all these inlets. So you go in and scan it. You don't really do anything with the scan of the cylinder head, but you can use those outlets to recreate a very accurate new intake manifold right off it. It's a very rapid process. And there's also a scan to inspection workflow. So you might scan a first article part and look for deformities. You might scan supplier parts and look at the quality. One thing I noticed as I was scanning this guy is these two shock towers, you would expect them to be in plane and straight, correct? And they weren't. I mean, looking at it, they look straight, and it would be really hard to tell that they're not just using calipers. But when I scanned it and I started to build files off this, I noticed instantly that these two things are warped. They're skewed. And so, you know, it might be small enough that it didn't affect the performance of this part, but that might not be always the case.
Is there a size limitation? So, I mean, can you scan an elephant, let's say? Or...
Yeah, you got an elephant?
No, not on me, but...
You paint our targets on it? No, there's not a size limitation.
What about the other direction? Say you want to do the tip of the pen and there's an internal feature on it.
Yeah, so that's where you are gonna see some size limitations, and that comes down to the resolution and what our smallest feature is that we can calculate. So some of the smaller parts on this guy, you know, don't have as good of data as some of the larger parts for that reason. We do offer two types of software. I wanted to just quickly discuss this. We have a VX model software, which is more entry level. It's CREAFORM branded. And then we have a software called DesignX, which is what I use. It's the higher end software. It's a little bit more robust, probably a lot more robust, pretty automated workflow. It does have full CAD capabilities, so it is a full CAD tool. I didn't really use it that way because I'm well versed in SOLIDWORKS, and it doesn't have the same capabilities as SOLIDWORKS does. And for that reason, it has a live transfer to SOLIDWORKS, to a lot of other pieces of a lot of other CAD tools as well. So you start to build some basic shapes in DesignX, and then you hit transfer, and it will transfer over to Inventor or SOLIDWORKS or Creo, I think, Pro E, and it will build a feature tree for you that's editable.
So are you actually using these meshes as a template to draw over the top of these things?
Yep, exactly. And you'll see a screenshot later on, but that's exactly what I'm doing. So I have a template, and you'll see how I'm actually using them.
So there's no scanner software to create my term of vector. Usually it's always a mesh. These softwares always turn these scans into a mesh.
It's a mesh. There is, within DesignX, there is like an auto surfacing tool where it will auto surface that mesh, but it's not usually, I mean, for my purposes, it wasn't what I wanted. But for some other purposes, it could be exactly what you wanted.
Yeah, because it wasn't accurate enough?
Yeah, I wanted very prismatic shapes in very definite shapes that are tightly controlled. Whereas when you do the auto surface, it's just, there's not a lot of control over it. Do you agree with that, David?
Yeah, normally with auto surfacing, it's usually for very organic shapes.
Yeah.
You couldn't draw otherwise. Unlike this comment about the prismatic, but he wanted to have features in the tree that you could edit.
Yeah. I wanted flat surfaces that are straight and square and whatnot. All right, so let's get into the process here. As we're going through this process of recreating this chassis, I want you guys to notice in the bottom right-hand corner, I have a little logo, and that logo is a signal as to what piece of software I was actually using. So this is the DesignX logo, and you'll see SOLIDWORKS, you'll see Stratasys, you'll see Inspire as well. So to reverse engineer this chassis, which is the first part that we wanted to do, we put this chassis, instead of putting stickers on the chassis and doing one single scan, we actually put this on a little turntable that we have, and that turntable has the stickers on it. So we didn't have to put any stickers on this. And we scan it, and then because it is on the turntable, you have to do multiple scans. So you scan as much as you can, you stop it, you flip it, you scan it again, you stop it, and you end up with, in this case, we did 4 different files. So these are 4 different scans. They all have a little bit different data based on how the part was oriented. We combine those scans using the DesignX software. We realign them. into a single scan, and then we remesh it globally. This process takes about 3 to 4 minutes. It's pretty easy. It basically says, here's your scans. Which two do you want to move? Pick corresponding points on each one. And it does like a coarse align, and then it does an automated, more accurate align, and then it just remeshes it all as one. And so actually what happens is you get a result that's basically a combination of 4 scans. And it's probably hard for you guys to see in the back here, but this scan is so accurate that you can start to see some of the sticker data on this. So this is a sticker that's raised just slightly. You can actually see it up on the bottom of there. So it's a quite accurate model. We ended up doing this for every single part in the car. So this particular chassis has a few parts that are already bolted together. We scanned every part individually because we felt like it gave us more flexibility in what we wanted to do. Like if I only wanted to recreate the shock tower, I could do that if I had it as a separate file. So we scanned them all individually. All of these 7 parts are actually what I created, what I call the chassis. So the chassis has all of the mounting points. So you have like control arm mounting points here, shock tower mounting points here. You have steering servos and steering bosses here, front bumper and front control arms, front shock towers. All of those mounting points, that's what I'm after. Because I know later on that I wanted to create something like this. I wanted to create a single part chassis. Okay? Are you guys following along?
You're confusing me with the term
Sticker. Like these guys here. You peel it off and put it on your part. Those are all known things. The scanner knows what they are, so it knows how to treat those. Yeah.
The turntable you said had the stickers.
Yes.
Is there any relationship between the turntable and the part? Are there you don't have to, if you're doing the other parts, or you're doing multiple scans of your base chassis, that doesn't have to be aligned again. You just set it down on it.
Correct.
So it's totally independent of each other.
Yep, totally independent. And actually, I don't know if Cameron has done this because Cameron did the actual physical scanning, but you can scan just the stickers only and tell it only pick up stickers, and that really accurately places those stickers. And then you can save that as a profile, and you can just load it up again. So when you did these, you just probably load up your turntable, and then you can just quickly start scanning your.
If you shut the top of the box there, you can kind of show that. Imagine that's your table right there. That's just pre-targeted, and then you just set a part on there, and then just scan it. The scanner sees the scanner sees the targets in the background, and then you're just able to scan. Now, if the part is big enough, you can put the targets right on the part. And then you can hold the part and just scan it. They don't have to be in the background.
So you're making a cyber container.
Think of them as GPS points, and that's how the scanner tracks. Because there is no ARM or gantry or X, Y, and Z of how it knows where it's located to line up the data. It does it through using the targets as points. They're all recorded, and then it lines up all the surfaces of the scan.
Yeah.
And this will distinguish the difference between the part and the table?
No, you would pick up the table in your scan, and then in the software, you just say, here's a clipping plane, and it just clips all the way down from there. You can just pick a couple points on that table and say, here's a clip plane, and it'll just delete the table out.
So it's below, I assume you
Yep.
like the Z axis.
Yep.
Ignore everything below.
Yep, exactly.
Are the stickers dumb? I mean, they're just a reflection point from the tool, so they're not any particular identifier in the sticker itself.
Correct.
It's just a relationship to the other stickers.
They have to be this particular sticker so that when the camera sees it on the scanner, it knows that it's looking at a sticker. But other than that, that's it. Okay. So I took all of those scans and I aligned them within the DesignX software, and then I started rebuilding some geometry. All right, so these are the points that I started rebuilding. Notice I didn't rebuild the whole car. All I wanted was the mounting points, because this is what I'm going to feed into the next step, which is the SolidThinking Inspire software, the topology optimization software. All right, so all I needed was all of these critical points here. I could rebuild entire parts, and I did that on some cases, but in this particular case, just the mounting points. And that gets us past the reverse engineering stage and into the design and analysis stage. So let's quickly show you guys a quick video here.
Where do your designs begin? Do you use previous projects as a starting point? Can they be based on hard-earned knowledge, or is it something else? When faced with a straightforward problem, like a beam carrying a single load, creating an efficient structure is something that can be done with, let's call it our engineering intuition. Or the same arrangement can be drawn here with all the simplicity of a sketch, and optimization algorithms generate basically the same elegant solution. But what if we tackle something more complex, like an assembly with multiple loads applied in 3 dimensions? For most, engineering intuition is not enough anymore, and conventional simulation tools won't help. SolidThinking Inspire changes the way design engineers approach design by generating forms based on a set of loading conditions. The results can be validated and compared using native analysis tools. Final models can be easily exported to your preferred CAD tool for finishing, or you can use the cutting-edge PolyNerves toolset to prepare the model for additive manufacturing. Inspire can help every design engineer quickly create dramatically lighter structures and better understand the effects of material placement in whatever they're developing. New users need, at most, a few hours of training, and many require none at all. SolidThinking Inspire. Lighter, stronger parts without the learning curve.
So who's already sold on that? Right? That's pretty neat, don't you think? The last part that they talked about, where it being a very accessible piece of software to get your hands on and start using, is absolutely true. So this project is the very first time that I've ever used Inspire. It's actually also the first time I used DesignX. So DesignX is has a little bit steeper learning curve. SolidThinking, very approachable. SolidThinking, it's a NURBS and Morphogenesis CAD software. So the Morphogenesis part is the optimization part. The video didn't show it very well, but we'll beat it to death later on. But it basically, again, it creates this design envelope with critical surfaces. You impart loads on those surfaces, and then it does an FEA analysis and iteratively whittles down to the shape that you want. They call it morphogenesis. Does anybody know what morphogenesis means? Where that term comes from? It's a medical term. It basically means bone growth. And so, you know, you can see that this software has been around for a long time. It was originally created by a research group looking to study how bones react to forces and how they might change shape based on loads, external loads, and how they grow in response to external loads. And those algorithms that they developed were basically turned into mechanical CAD software because they thought, hey, we might be able to create optimal designs out of that. What ended up happening was it didn't become very popular until the last couple years when additive manufacturing became more accessible as well. Because especially early on, the results that came out of that software were very organic. They were not optimized for any type of manufacturing and often created shapes that were not manufacturable at all. Okay, so there's 2 things that happen. One, additive manufacturing changed what is manufacturable cost effectively. And 2, the software got a little bit better to the point where we can now impart things called shape controls and sort of guide the results towards a type of manufacturing. So I can say, have free reign and give me an organic freeform shape, or I can say, give me a shape that has just straight zero draft, more like an extrusion, something I might want to machine. Or give me a result that has draft in a single direction, or give me a result that has draft in 2 directions. All right, so if I know, even if I'm not going to be 3D printing this, if I know I want to machine a bracket, I can tell it only give me results that might be machinable. So a quick intro into what topology optimization is. I like to call it it's true design for additive manufacturing, because the most optimal results are typically impossible or difficult or not cost effective to create. The engineers define the boundary information and not the shape. So this is a fundamental difference in going back to our bracket, how we might approach the design. In the old style, the engineer defines the boundary conditions and then creates an initial shape and starts doing some detailed drawings, does some FEA analysis changes the results based on that. What this does is all the engineer initially does is create the boundary conditions, set up an FEA study. The software then tells him, here's an optimal shape that you should go with. And then it's the engineer's responsibility to take the information that the software tells it, which is all the software is doing is saying, here's the shape that you want. These are your load paths. You absolutely need material in these spots. You can add more material other places. And I don't care how you put the material there. I don't care if it's machined or cast or welded or 3D printed. Just put material here. Does that make sense? So it eliminates that first pass, that first guess. Types of inputs that they're going to use are support faces, forces, pressures, RPMs, accelerations, both just straight and circular accelerations, thermal loads as well. And really just keep in mind that the software is outputting the load path. So it's showing you, based on the resultant forces from all those load cases that you did, this is the result. These are the forces. This is the paths for the forces. Notice I use the word load case. That's pretty important. It allows you to set up, like in the example of our car, we did an acceleration load case, we did a decelerating load case, and we did a sharp turning load case. So all of those load cases have different forces, different accelerations, different pressures, stuff like that. It solves all three of them at the same time and gives you a result that's optimized for all three of the conditions. Okay. Some of the characteristics that we can optimize for, max stiffness. We can target a particular mass if we need to hit a certain poundage. We can optimize around resonant frequencies, and we can optimize for wall thickness as well. And then keep in mind the shape controls that we have. You can go organic, you can do extrusion, or you can do the drafted ones. I know I mentioned that I looked at a lot of different pieces of software. This is one of the key reasons why I chose the Inspire software for us to actually involve ourselves with, because the other tools didn't have these shape controls. And most people aren't printing end-use production parts right now, right? Everybody wants to. We're not quite there yet. We're still using prototypes. Prototypes are the main application for 3D printing, and then we go on to injection molding, we go on to machine parts. And if you don't have these shape controls, then all of these steps are kind of superfluous because, you know, it's giving you a result that you're not going to create out of 3D printing, right? So shape controls are super important. All right, so now we're inside the Inspire software. What you're looking at, the gray areas they came from the DesignX software. Okay, so from DesignX, I just output a Parasolid file and brought it into, in this case, SOLIDWORKS, and I created my design envelope inside SOLIDWORKS, which is the maroon color. So that's my bounding box. This is a piece of information that I have to feed it. This is probably more complex than it needs to be. In general, Inspire wants a very basic bounding box. It wants a lot of freedom, you know, because I kind of built in some weaknesses within this, like not having any material right here created an inherent weakness in it, where if I had material within my bounding box, I'm sure it would have bridged that gap. Some of the load cases I did, so acceleration, you can see some of the forces I input. There's an acceleration down here going this way. You have remote loads for where the wheels make contact, and remote loads for where the end links actually link up to the chassis. I will say these load cases will probably not hold up to a lot of scrutiny. So if you get these, you guys already have these slides. If you start looking at these and say, this doesn't quite make sense, it probably doesn't. But it brings up a good topic. The results that you get out of Inspire are only as good as the information that you feed it, right? You guys definitely understand that, right? Same with any standard FEA analysis. If you set up your analysis incomplete or incorrectly, you're going to get an incomplete or incorrect result. Same thing for Inspire. So definitely put a lot of work into making sure that your load cases are accurate. We did a hard braking or decelerating. You can see a lot of forces on the front shocks or front wheels, a deceleration. One of the cool things, if you don't know the exact values, if you are optimizing for the max stiffness or the max rigidity, you only have to have relative values on your forces. So in reality, what I did was, since I didn't have hard numbers, I sort of just guessed and said, okay, when it's decelerating, I might have a force of 1 pound on the rear wheels, but 5 pounds on the front wheels. The 1 and 5 aren't really maybe accurate, but what I was going for is a force that's 5 times higher than the one on the rear, okay? And it's still going to give me the result that I want if I'm optimizing for max rigidity. If I was targeting a mass, or if I was going around resonant frequencies, or if I was really wanted good information out of like my factor of safety plot or my displacement plot or stress plot, then I would have to have more accurate values. Is everybody making sense? Does that make sense? Everybody following me? I probably shouldn't admit I did that, but I think it's a key thing to understand. Sharp turn, same sort of thing. We start to see some torques on the steering columns, some forces on where the steering servo mounts. We got an acceleration going this way. I also did a shape control called symmetric. It's basically just a symmetry plane. This made it so I didn't have to, say, turn both ways in my load cases. So it does, the first thing you do is run an FEA analysis, and this solver is pretty quick. If it's taking longer than 5 minutes, then you probably are running it too coarsely. So it's very quick, and it will give you a lot of the standard plots. This is a displacement plot. Like I mentioned, it will give you stress, it will give you factor of safety, a lot of the standard plots. In this case, I wasn't really looking at the values, but I was looking at, again, the relative movement between the spots.
I have a question.
Yeah.
The software will give you this animation and show you this, yeah?
Yeah, this is just a, this is actually just a screen recording of the results.
And it will give you the motion like this, yeah?
Yeah.
And that's all built within the Inspire software, right? You're not running it
Correct.
separately and then importing
Correct.
it.
Everything in here is still within Insight. So I'm just recording my screen within Insight right here. This is also within Insight. So you do a first pass, that's the FEA study. You might never go to shape optimization, but most people would. This is the next analysis. This analysis, again, if it's taking longer than 15 minutes, you're probably doing it too coarse. So it's pretty rapid. What you're seeing here is a screen grab of me moving a slider in the software. And that slider starts at 100% dense design envelope and then goes down to a minimum dense design envelope. And so you start to see the material whittle away. And what I'm looking for as I move the slider is, at what point do I see the minimum amount of information that I need to go on to the next step? So it's sort of up to my interpretation. Somewhere in the middle there, I saw enough load pass that I could say, okay, I have enough to actually design off of, okay? And that's where I started using that polynerves tool. So you guys got a kick out of that. When it started within that video, creating those swoopy shapes along the load pass, did you guys notice that? That's called direct editing, the push, pull. You can grab faces, edges, points, pull them, shrink them, expand them, add more for more control, delete them to make it more swoopy. That's built into Inspire, and it's awesome. I've always been a mechanical CAD guy, so I haven't done a lot of this type of modeling, but I've seen it, and I've always wished that SOLIDWORKS would implement it. Now I finally have this tool. Because if I wanted to draw this in SOLIDWORKS, or Inventor, or CATIA, or Pro E, this shape, kill me, because it would be horrible, right? It's a different type of modeling. And it took some getting used to, but, you know, again, this was my first project, and it came out pretty well. You've used Inspire. Do you have the polynerves tool? It just came out in 2016.
I haven't seen that.
You wish it had it, right? Have you updated to 2016?
No, I just used the trial.
Oh, got it.
But I
Got
a
it.
lot done in the trial.
Yeah, that's the way to do it. I'm pretty sure anybody can go on the website and get a trial. This polynerves tool is awesome. So what I did was, within Insight or Inspire, I drew half of it, okay? And then I brought it over into SOLIDWORKS, and I mirrored it. I combined those, and I started doing all my detail work in SOLIDWORKS, okay? So I needed to make this manufacturable. You know, I put these tapered holes in there to use these little brass threaded inserts. You guys notice those on the printed parts? It's a great way to get threads into a printed part. I added a few details, little artistic freedom there. But this is the end result. All right, so the idea here is that when I drew this, I probably had a particular material in mind. I would know the strengths of those materials. I can also put that material in Inspire. And if I do the exact same studies, but one I set the material as like titanium, or one I set it up as, say, nylon, those load paths are going to be the exact same. They'll just be different diameters. Does that make sense?
How big of a range of materials can you choose from in software?
That is a good question. I noticed a couple dozen, and I'm quite sure that you can input your own, but I'm not 100% certain on that.
Would you have to bring the strengths of the materials into the software? Or
If you're creating your own, yeah, you go to like MatWeb and pull up just some basic stats on it, because it's not doing like a non-linear sort of FEA analysis.
This is not specific to any manufacturing process.
This
right?
isn't. This is not.
Right, that's just sort of a general idealized frame.
Exactly. Because I knew I was going to be printing this and I wasn't going to do anything beyond that. Because I'm basically using it for brand visibility, for marketing. It's a showpiece, so I'm just going to print it.
You are impressing me with a lot of information.
Thank you. I appreciate that.
But if you had in mind, well, we're going to die cast this, would the results be different?
The results would have been different because I would have put a shape control on it that was like a double draw shape control. So it's going to be drafted in two directions, whatever I do. And so the result would be different. I will say, because this single part is such a complex part, the results might not be what you want. I will say Inspire is definitely geared towards more simplified parts, I learned, because this is a very complex part. We had, like 20 different mounting points, all in sorts of weird configurations. That part's going to be hard to manufacture no matter how you're doing it, right? And so what you'll see is the results for some of the other parts that I did, like the control arms and stuff like that, much cleaner results that would be more optimized for something like die casting.
Yeah. So if you choose, say, the double draw for an injection molding, does this also include a simple mold flow analysis on it?
It doesn't. Okay. It doesn't. And that brings up a good point. Now that I've drawn this and I have it in SOLIDWORKS, so it's all parametric modeling stuff, ideally I would set up another FEA study, a second pass FEA study, and verify my results. Okay? That would be the ideal situation. Because that Inspire FEA, it's a good FEA analysis, but it's not as robust as SOLIDWORKS or some of the other tools, and it definitely won't do mold flow or anything like that. All right, so now it came time to start prototyping this. We use the Stratasys machines. Between all the vendors that we talked about today, I think Stratasys is the one that you guys are most familiar with. There's your 1989, Tom. I could have got a water bottle out of that.
That's cheating.
I know, right? He probably stole it from me. All right, so one thing I did want to mention, because I just learned this fairly recently, is that last year in 2015, amongst all of the commercial 3D printing manufacturers, Stratasys sold over 50% of the machines that were sold globally. So they're the #1 machine manufacturer on the commercial level. And us at GoEngineer, in 2014, we were their #1 reseller. Last year, we got bumped by a reseller on the East Coast, but we were still, so we were #2 last year globally, but we're still #1 in maintenance renewals, which is, I'm pretty proud of that because it tells you that Stratasys is in a lot of different industries. They work with a lot of different customers using their machines for a lot of different applications, and we're right at the forefront of that. I'm very lucky to have the job that I do because I get to learn from people like you that come with all different backgrounds. Some of you might be, working on assembly plants. Some of you might be creating toys. Some of you guys might be creating jewelry and artistic stuff. And I learned from all of you, so I love it. So 3D printing, who in this room has not 3D printed something? I had to change that question recently because I used to ask who's been 3D printing stuff. Everybody would raise their hands. And that's changed a lot over the past couple years. More and more, I have to talk less about the basics of 3D printing and we can talk more about the applications. But I still like to cover the basics because it's important. At its most basic, 3D printing is an additive manufacturing technology, as opposed to something like machining, which is subtractive. Okay, so in a subtractive situation, you're going to start with a block of material, and you're going to use tools of various shapes and sizes and materials to whittle down into your end shape. And that limits you in the types of parts that you can create. It limits you in the flexibility of your designs because you have to work around setups, work holding, tool accessibility, other typical design for manufacture rules. Whereas with additive, what's that?
Lunch.
What's that?
You have to work around the brick.
Oh, yeah. In America, we don't have lunch breaks.
Yeah.
No, you do have to work around lunch, and 3D printing is great for that because 3D printing is like a lights out manufacturing tool. You hit the button, it goes, you go do something else. We keep these machines running 24/7. Most CNC machine shops do not do that without a person at the machine, an operator that's in charge of loading the materials, doing their precise setups, unloading the materials, adjusting the feed rate as that machine's going, listening to it. We don't do that. We hit go. I time it. Personally, I time it where I get in the morning, I unload the night before parts. I hit go. I try to print enough parts to get me to the end of the day. It stops. I unload it. I load up more parts that gets me through the night, and it just goes. And then comes the weekend. I get to do my big parts. I get a 3-day weekend. I get to do the bigger parts that are usually toys and stuff like that. So we keep these going. There's no drawings. It's all digital. We go straight from the CAD file. And it's super accessible. This is one of the best things about 3D printing, and it's one of the reasons why it's exploded over the past 5 years, is anybody in this room can become a manufacturer with a 3D printer. Everybody. With a little bit of investment in machinery, not really any investment, depending on your machine, into where you're going to put the machine and all of the supplemental equipment that you might need. It's all very minimal. Anybody could be manufacturing parts. When I did this in Salt Lake a couple days ago, and I had somebody raise their hand that he said he designed a exhaust manifold or a turbo manifold for a Hayabusa motorcycle. He had somebody scan an existing one, pretty similar process. He designed a new one. He paid somebody to 3D print it. They used that 3D printing tool at the foundry to create the tooling for that. And he has a business now. And it all came down to the tools that he used. Scanning, CAD, the printer, and then he found a partner in the foundry, and he's selling these exhaust manifolds. The tooling alone was about $19,000, and that didn't include the printed part. If it included the printer part, he told me he wouldn't have been able to go down this venture. It would have been too expensive. So the printer actually enabled him to create that business. We see that in all sorts of different industries. But I guarantee you, if you haven't used a printer, I could teach you how to use a printer in about 2 minutes. If you know how to print a Word document, you know how to print any single part that you see on that table. So I'm going to start with FDM.
Precision modeling is a 3D printing method that makes durable objects out of the same plastics you see in everyday products. With FDM, the 3D printer takes a spool of plastic filament, melts it, and extrudes it onto a tray to build a part layer by layer from the bottom up. FDM materials are all industrial-grade thermoplastics. That's what makes the resulting parts so tough. And it's also why FDM is changing the way industries design and manufacture. With FDM, a designer can sketch an idea and test it the same day. Industries can cut lead times and costs. Products turn out better and get to market faster. FDM parts are helping to build the cars you drive. They're in the airplanes you fly in. They're in the medical devices that save lives. FDM is cutting waste in manufacturing. It's helping engineers power remote villages in Africa. It's helping farmers feed an ever-expanding population. And the ideas keep coming.
Doesn't that video just get you pumped up? He's so excited.
It makes me very nervous.
He makes you nervous? All right.
No, we spend millions of dollars developing products, and you have a device there that someone can copy my product instantly.
That's true. That's true. And that's why we have copyright
Are you saying that
and patent and intellectual property laws.
the machine that printed the chassis,
Yeah.
it was a single filament machine,
Yes.
no support material required?
Okay. It has a single model filament and a single support filament. You'll see in pictures there is support material. If there wasn't support material, I would have had to probably change my design a little bit.
When they took over MakerBot, did the line that MakerBot was producing change much? Did they sort of blend the two companies in a way that they both one and maybe lower end as opposed to the other, or is
they still
distinct
function
product
quite
difference?
separately. Quite separately. So Stratasys actually has a few different segments. It has their commercial machine manufacturing and selling. They have something called Stratasys Direct Manufacturing, which is like print-on-demand service bureau. And then they have MakerBot, which has retained its own identity and pretty much operates autonomously. The reason why they did buy MakerBot, any guesses? Anybody know that story? Yeah, exactly. So a lot of times when we come into a room like this and we present, you say, okay, I'm convinced on 3D printing, but it's going to be a hard sell for me to fork out $20,000 to $400,000 for a printer. Is there a machine on the market for $2,000 that I can maybe get my feet wet? And that's what MakerBot was. And so MakerBot has a long history, but it became the #1 hobby level machine. And so it was the #1 machine on that small price point. And we saw engineers and designers bring them into work, use them, and get some good parts out of them, but also deal with some frustrations. And when it came time to say, okay, we're convinced on 3D printing, we see the benefits, it's time to upgrade, who are they going to go to? Well, if Stratasys owns MakerBot, then maybe they'll stay within the same family. So that's what the strategy there was. I think it's been pretty helpful. Most of the parts that you see on here, I printed on this Fortis 250 or the Fortis 450. These are just, I'm not going to go into the details on the machines, but just know that there's pretty much a machine at every price point that you can imagine. So what you're looking at here is a glimpse of inside the printing software. When I go to print a part on FDM, I have to choose a material and choose something called a slice height, which is the Z layer resolution. I also have to choose an orientation. And with FDM, orientation is probably one of the most important decisions that you have to make. And so when I printed this, I actually printed it upright on its side like this. Anybody want to guess why I might have chose that orientation as opposed to like this or like this? Yeah, so that's a pretty good indicator. So I knew it was weak, like bending like this, right? And so what I wanted to do was either I didn't want to impart a force that would cause it to shear along the Z axis. Okay, so with FDM, you essentially have parts with thousands of Z like shear layers. Yeah.
How much weaker is the Z axis compared to the X and Y?
It depends on the material. It could be as little as 10% to 25%. Okay. Nylon is going to be the most isotropic, and then the other ones are pretty universal, like pretty much the same. But nylon, for some reason, it's a little bit more uniform. And then any other reasons why I might have done it on its side? Because if I printed it standing like this, I would still get the Z layers that I want. I think it took a little bit longer.
Your Z-axis is usually your worst tolerance level.
That's true.
And
that's true.
It would tend to distort those features a little more.
That's true. That didn't come to mind in this particular case, but you're absolutely true. So in Z, because I printed this at 10 thousandths slice height, my Z layer goes in increments of 10 thousandths. Okay. Whereas in XY on the machine that I printed on, it's plus or minus 5 thousandths. So it's more accurate in X and Y. Aesthetics was really the reason. It looks better standing up. Okay, so with FDM, because you have these discrete steps, as your walls shallow out, those steps become more pronounced or more visible. So you really want as many vertical walls as possible. And that's why I chose it this way, because I have lots of vertical walls as opposed to flat, where this bottom is very shallowly rounded. Does that make sense? So it just creates a better looking part.
See this?
Sure.
How many hours?
Oh, that's about an 18-hour build. So, you know, it's 18 hours. I started it one day and I had it the next day. Notice, go ahead.
Just gonna, on the bottom plane, they generally have like a heated platform because of, is it temperature distortion of the material?
Yep. So all of the Stratasys machines are basically ovens. They're all enclosed, and they're all very tightly temperature controlled. And on the larger machines, they have very tightly controlled airflow as well. Because what you don't want is your part cooling at different rates, and because it's going to start to warp and start to have dimensional issues. And so everything's very tightly temperature controlled in these machines.
So I was wondering if that came into effect of also standing it up on edge as opposed to bottom layer.
It shouldn't. There shouldn't be a temperature gradient amongst, like, in the different Z layers, because they have fans and they have air circulating and whatnot. I didn't have to worry about creating uniform walls because one thing I knew I was going to do is I was going to print the interior sparse. So you guys can see the density of the print actually changes as it goes up along there. You have like a solid, you have a semi-sparse, and you have a sparse area. That helps on weight. It also helps on material usage.
What's really neat is if you look at locomotors, what they're doing with their car bodies is they're hollowing it out now to meet crash tests. Because otherwise, with the first ones they printed, you slam it in the wall and it'll be like a 57 Chevy. It's not going to move.
Really?
So now they're making crumple zones within the structure, just like we're showing here.
That's very cool. That's very cool. Yeah, so this is just like a click, you know, this is not drawn, this is drawn solid in the model. And so it's just like a one click. I don't have a lot of control over the interior shape, but there have been prints that I've done. I've actually modeled a surface and I've done interior portions as well. And that's probably what they're doing, where it's a more structured interior. Totally possible. Here's another screenshot from that software, and this is the support material that you were asking about, all the gray. Yeah.
This is the software within like a Uprint or a Fortis.
Yeah. This is called Insight. Insight, because I use the Fortis machines. The Uprint uses Catalyst.
Yeah.
And Catalyst doesn't have as many options as Insight does. For this particular part, I didn't do anything special, but in a later part, I needed Insight to do some of the stuff. Yeah, you can do like hexagonal patterns. You can do some other stuff. I wanted to show this because here it is standing upright. 3D printing, you know, I've told you it allows you to print pretty much every shape that you could imagine. So what does it do when it needs to print like an overhang or an internal cavity? The software sees those unsupported surfaces and creates something called support material, and it prints that out of a different material. So the reason why it needs to be there, if I go to print this guy and there's nothing there to lay it down on, it's just going to fall, right? So very critical component to have. Here's a picture from inside the machine of that chassis that you're holding. There's your black. That's a PC ABS, polycarbonate ABS blend. And then the support material is like this root beer colored material. This is water soluble. So after I take it off the machine, I'll usually break off as much as I can. And then I'll put it in an ultrasonic bath that we have. And the ultrasonic bath it's just a mild sodium hydroxide mix, water that's heated, and it dissolves that away in a couple hours. So it's very hands-off, but it does take a little bit of time. All right, so that's the story of the chassis. Did you guys catch every one of those steps? The reverse engineering, the design or analysis-driven design, the detailed design, and the prototyping. So now I actually wanted to use this as a prototype. You know, it's durable enough that I should be able to print more parts or hook up more parts and actually drive it around. So it's time to accessorize. We're going to start doing some other parts. Every single one of these parts is going to follow this same workflow, so I'm going to not go into as much detail as some of these other parts. I started with the control arms. We did the same thing. We took 3 different scans, combined them, remeshed them. These different colors, this is also in DesignX. What you do is you say auto region this, and DesignX looks at the mesh and it identifies things like planes, cylinders, cones, revolves, sections, and it allows you to interact with those. So when it came time to actually redraw my geometry, I can say I want to draw a sketch and I want to sketch it on the plane that's red. And then it allows me to start sketching on that. What it looks like when I say I want to sketch, you'll see a screenshot later, but essentially what it does is it takes a plane and it puts it down somewhere in the model, wherever you tell it, and it picks up the silhouette of the mesh at that point, and then you use that silhouette to redraw your own sketch entities. I wanted to modify these a bit. I wanted to give it a little bit wider stance. So once I came into SOLIDWORKS, I moved one of those mounting surfaces, and then I built my design space. I made it very basic as possible. Then it gets loaded up into Inspire. I did my 3 different load cases. I have basically acceleration, deceleration, and turning. Different torques, different forces on the shock mounting spots. I do my FEA analysis, and then I do my shape analysis. This particular analysis I did in extrusion shape control. And so that's why everything's pretty much straight down. Okay? So this is the ideal shape based on my, I shouldn't say ideal shape. It's the most efficient shape based on my load parameters. Then it comes time for me to start redrawing these or using that shape recommendation to draw my own parts. I did 2 versions. I did an organic version with the PolyNURBS tool, so that's the center here. Notice I added a member. Anybody want to guess why I did that? Yeah. Well, kind of. It didn't look right. Like intuitively, it didn't look right, you know? And so this is another thing that I wanted to mention, and this is something that anybody who uses this software is going to have to battle with, is sort of trusting the results. You know, how accurate was the load cases that I input? And I just wasn't really sure of it, you know? And it gave me something that looked unintuitive. So on one hand, there's no harm in me adding a little bit more material. Maybe it's a little bit less efficient. In reality, what I would do, if I had a little bit more time, I would create a version with it and without it and test both of them, all right? Or just continue on with the suggested, and then when I get to my follow-up FEA analysis, maybe I'll find something out there. Okay? But I think you guys all understand, like, this software is maybe going to give you some stuff that's unintuitive, and at a certain point, you just have to trust it. It's probably going to take some experience with it, and knowing that what sort of results it gives you and knowing how well you set up these load cases before you start trusting it completely. So I did my PolyNURBS, and then I took it into SOLIDWORKS and did the detailed design. I also created a machined version as well. Then I printed those guys out. I think I just printed this out of, I think it's still PC ABS. I didn't have enough space to use the threaded inserts, so I just strictly threaded the plastic. Another thing that I did, where I figured out that these were probably the weakest spots, because how thin that material is right there. With FDM and with any 3D printed material that's going to react to a solvent, this is a little trick to make it a little bit stronger in small things like that. You use something called plastic weld. It's just a solvent cement. It's very, very thin. You can paint it on there and it gets sucked down into the part. Just capillary action just sucks it down in there, and it helps solidify that part a little bit more, makes it a little bit stronger. So nice little trick there. Acetone wouldn't do the same because acetone isn't a cement. So acetone might melt is probably the wrong word, but it
eat away.
So what it will do in small amounts is acetone will melt it and maybe get the layers to combine a little bit longer, but you're still relying purely on the mechanical adhesion of the plastics and not the cement.
It's more of like a CAD.
Yeah. Yep, exactly. If I was going just for appearance, on the outside, acetone would work pretty well. It'd smooth it out pretty well. I did the rear control arms. You can see the scan. I did an organic version. This one I did follow very closely with what it recommended. And then on the machine version, I didn't. I wanted to do a rear spoiler. And so to come up with this initial shape, I just found an off-the-shelf airfoil shape, flipped it upside down. I wanted to give it a little bit of curve, and there's not a lot of SOLIDWORKS users in here. But I wanted to show this slide because I used a tool within SOLIDWORKS that is not very often used. It's called the Flex tool. And what it allowed me to do is I wanted this airfoil to be curved. In most CAD tools, if I wanted that curved profile, I'd have to do sketches and then do a loft between those sketches. What the Flex tool allows you to do is just draw it straight and then flex it or bend it. It also allows me to twist it and do all sorts of stuff. I don't have quite as precise control over the shape as I would with a loft, but in some situations, it's exactly what you want. Yeah.
What file format and what does your design tree look like when you have that in SOLIDWORKS?
This particular file?
Any of them.
Any of them? Okay, so going back to the chassis, from DesignX, I saved out a Parasolid file. Parasolid is just a generic file that's pretty universally used on any software that uses the Parasolid kernel. If I was, another option would be like a step file, would be my second option. That goes into Inspire. From Inspire, I also saved out a Parasolid file. I brought it into SOLIDWORKS. So the very first feature on, say, the chassis was an imported body. All right.
That's like a dumb brick.
The initial dumb shape is. Yep. So you're losing the parametric version of that.
You have no design.
No, I do have a design tree. And in fact, my design tree for this guy was like 400 features. Because maybe I'm a bad designer. But that initial shape was dumb. What ended up happening was, if you guys look closely, that black chassis has an issue with the steering. The steering doesn't clear right here. There was two arms that I put in there initially that didn't clear. This one obviously has clearance. I did not redesign this whole thing. This was a little bit clunky, but what I did was went back to Inspire, deleted those arms. I wanted to make the edit in Inspire because as soon as I delete an arm, everything else sort of still retains like that fluid shape, right? I cut out just that section, re-imported just that small section into SOLIDWORKS, and cut out the front of the SOLIDWORKS model and brought in my new body. So the only thing I had to redo was a couple tapered holes that I had done. So not the most elegant, but again, this is a lot more complex than most parts, okay? So if you're using it to be used more as it's intended with brackets and other shapes that are a little bit more simpler, or more, say, straightforward, you're not going to have as much of an issue. Does that make sense? I wish it ran inside SOLIDWORKS, but it doesn't, because it's using a totally different technology. All right, so what I was going to optimize for the spoiler was the mounting area. I brought this spoiler shape into my SOLIDWORKS assembly and oriented it where I wanted it relative to the rest of the car. I tilted it, placed it where I wanted it. And then I picked up the mounting points from that assembly. So in SOLIDWORKS, we call it an in-context feature. Then I opened up the part file and I drew this working envelope. That's what I loaded up into Inspire. The only thing that's different that we haven't seen on this is something called a force displacement load. What a force displacement load is, I'm basically saying this bottom edge has to move a certain amount. Okay, this is actually a really cool load case, because if you think of something like a buckle or a snap fit, where you know it's going to deform a certain amount before it springs back into shape, you can just tell it that you have to move 1/10 of an inch. You don't have to figure out the loads that it would take to displace it that much. These are the results. I looked at this and I thought, I can't really redraw that with the polyNURBS. I don't know how I would improve on that in SOLIDWORKS. So I just saved it as is. That's another option that you can do. You can just save that result as is. And when you look at that, actually I'll pass this spoiler around. You can see within the print, you see those same bumpy surfaces. I just used it as is. When it came time to print this, I printed it straight up. again, mostly for aesthetics reasons. I wanted surfaces that were going to be as vertical as possible. One change I made was to the support material. So it needed support material all the way up to this mounting area. But the way these printers work, it can only print one material at a time. And it prints 2 layers of the same model, and then it does a quick, relatively quick tip change over to support and does those 2 layers. That tip change happens every 2 layers, and it can take 15, 20 seconds. And so when I first processed this was probably a 12 and a half hour build. By changing this material to model material and eliminating those tip changes, it went down to about an 8-hour build. So there's absolutely no difference, just a little bit of tweaking in the software. So that's where the benefit of knowing the ins and outs of this Insight software can kind of help. The cost of the material is the same. No downside of doing that.
And that's something that's exclusive to Insight. Right?
It's exclusive to Insight, so you wouldn't get that in the Catalyst software. All right, the last part that I looked at was the wheel. Look at that scan, just real quick. I just love that scan. The treads on that wheel are so crisp. I was really impressed with that scan. Same sort of thing. Design space, critical surfaces. I set it up in Inspire. A couple new things that we haven't used. We have the double draw shape control, so that's the dual draft. I did an RPM load. So I figured out, based on the diameter of this wheel and the advertised top speed of this guy, which is about 60 miles per hour, came out to about 3,000 RPM. I just did a strict 3,000 RPM, but I could also do an acceleration up to 3,000 RPM as well. Force load for the spindle, and then also a cyclic symmetric shape control, basically meaning it's going to be symmetric around the center of there, and I could tell it how many legs I want it. Here's the result. I thought this was basically predictably boring, and I had already used a bunch of these, so I just didn't use it. I could have printed it as is, and it would have been a pretty good result, but I thought, man, that just doesn't really showcase what printing can do. And we hadn't talked about PolyJet yet, so I did an airless tire design. You guys, this might look familiar. But the cool thing about this is I knew I was going to print it on our Connex machine. And our Connex machine, instead of using that filament, it uses a resin with a print head. And the same way that your printer at home can print red next to green, this can print Shore 45 rubber next to Shore 65 rubber-like material next to, say, Shore 85, and it can do different colors and stuff like that. So I was able to create a wheel that is gradually stiffer as it goes down towards the interior. But that's all one print job.
How do you get the 3 different types of shore to bond with each other?
That is the responsibility of Stratasys and their design. So, these are pretty similar materials. Actually, what you're seeing is 2 materials that are mixed at different ratios. They're laid down as a resin, and then they're hit with a UV light and cured, and they bond together. It has to do with the chemistry of the materials, so I don't have to deal with that. All I do is put it in the machine, and it does the magic.
PolyJet is a 3D printing method that makes beautiful, precise models in a huge variety of materials and colors. It works like an inkjet printer, but instead of jetting drops of ink, PolyJet 3D printers jet tiny droplets of liquid plastic. A UV light instantly cures the plastic, solidifying it. And so, layer by layer, complex models take shape. The most advanced PolyJet systems can build multi-material parts. Soft, rigid, clear, and colorful. You can even adjust material properties like heat resistance and durability. The same technology that makes gorgeous prototypes also makes precise manufacturing tools. Designers can predict future needs and serve them now. Manufacturers deliver better products faster and with less waste. Researchers have new methods of saving lives. PolyJet is reshaping industries like film, fashion, and medicine. It's helping people with great ideas improve the future. What's next?
All right, so you guys will notice as you hold those parts that the surface finish is a lot better, the resolution is better, The size of the features is smaller than what we can do in FDM. The materials aren't quite as robust as FDM. We have lots of different machine options just like we do on FDM. Some of these machines, like the desktop series, will only print one material at a time. So the second parts that I just handed out came off a smaller machine. And then the wheels came off a Connex 3, which you can load 3 different materials, and it will let you print them side by side, or it'll also let you combine them, and that's how we get the different shore values. We have a new machine called the J750. Anybody heard of that yet? It just got announced a couple weeks ago. I'm telling you, it's the coolest printer I've ever seen. It's like a Connex 6. So you can load up 6 materials, which means you can do clear next to full color, because you can load up to 5 or 6 different colors. It gets you over 360,000 colors. It has different software too, so you can actually load in a color map or a texture or a VRML file. So if I wanted to print like a skid plate on the bottom of this guy, and I wanted to make it look like carbon fiber, or if I wanted to make it look like wood grain, I can go into Adobe, put that color information on that, and then the J750 will read it, and it will print out the full color. I don't have to do separate bodies and place the color. I wanted, even though it didn't have anything to do with this, I did want to show you guys a print from the J750. I can't wait till we get ours. I have so many plans. The color thing is huge.
Can I ask a quick question?
Yeah.
Will that print urethane?
No. No. Urethane is, no, it won't.
Okay.
These are all acrylic or methacrylates.
Those cure, but they break down over time. They're not meant to be like forever.
Well, forever is a really long time. A really long time. They are UV cured.
What's the life cycle?
So, I mean, Tom, you have parts in your case that have been around for years, right?
Correct.
If I were to put this out in the sunlight and keep it there for an extended period of time, it would change shape. It would also become more brittle because they are UV. They're not UV resistant, right? Because they're UV cured. As soon as you coat that, that changes. But they're also not quite as temperature resistant as the FDM parts. So if I left this on the dash of my car on a hot summer day, if you guys have those here, it would change shape, okay? So, you have 2 different technologies. They both have their places where they fit best. And for this type of stuff, prototyping is usually the best fit. But some tooling as well. I did want to show you guys a screenshot within the DesignX software. We pretty much talked about this, but recreating these, the differential case, these maroon lines are the silhouette at a particular spot. So I wanted to bring it in. I drawed my basic shapes in DesignX. This is what it looks like when I'm talking about using the scanned data as a guide. I get the profile. I draw my own lines. It will do best fit lines when you want them, and it will also allow you to draw your own lines. So you're using it as a guide. It will snap to points and stuff like that. So the basic workflow looks like something like this. You start using it as a guide to draw the basic shapes, and then you would take this basic shape, at least this is how I did it, and took it into SOLIDWORKS and did the more elaborate drawing. DesignX is a full CAD tool, so you could get this drawing inside DesignX, but I've just worked where my strengths are, so I brought it into SOLIDWORKS. We do have a couple of these prints there. You can see it's got bearings and whatnot. It's a totally functional prototype, even though it is PolyJet. And we're pretty much there. We've got the car up here, so if you want to actually see it, I do have the battery, and it has a little bit of power, so I might drive it around a little bit. It does drive. It's not that impressive. I mean, the thing is impressive. If I drove it into the wall, it would destroy itself, I'm sure. I don't want to do that because I have to do this presentation in Portland tomorrow. All right, so that's pretty much all I had for you guys. Go ahead. Did you have a question? Okay. Does anybody have a question at this point? That was a lot of content, wasn't it? What do you guys think of that workflow? What do you guys think of the individual tools that we used? Any feedback?
The Inspire software is good. It takes like everything that Materialize will sell you individually and puts it into one package.
Yeah, exactly. And Materialize is more geared towards 3D printing only. where this tool is not.
And it's nice to see the options. You have literature on that here, right?
You know what? We don't have any literature on that yet because we just met with these guys literally like a month ago. But I can get you some stuff. Like I'll have my cards here, or you can just shoot me an email right there, and I can get you anything you want on it. Yeah.
All said and done, how long from conception to final product did it take?
Too long. But here's the disclaimer there. This was my first time using DesignX. It was my first time using Inspire. So I was learning 2 softwares at the same time. This was probably an 80-hour project. Okay. That's what I told my boss anyway. It took longer than it should have because I was learning 2 new softwares, so I was not efficient, and I got better at it. You know, I was learning the softwares. It was also the first time I did the push-pull type of modeling, and that took some getting used to as well.
What is your background, if I may ask?
My background is in mechanical engineering and medical device manufacturing. All right, lunch is here. As you guys are grabbing your lunch, I think Cameron's going to set up the scanner and show some live scanning demos. I definitely encourage you guys to stay and watch that. If you are time pressed, that's okay. We're going to be around here with if you guys have any questions for Tom or myself or Cameron or David. You guys already have a copy of the slides. I did make a quick couple edits this morning, Tom, so I'm sorry. Those slides there's a couple typos in there. And but if you guys have any other questions at all about what I showed you or maybe why I did something, or if you just want to tell me how poorly I did something, you guys can shoot me an email as well. So thank you guys for coming.